All right. So sorry about missing class again today. Things happen. We have to do what it is that we have to do. So, anyways, so this is to make up for what we missed in class today. So this is hopefully going to replace what it is that we should have done in class today. Um, so hopefully you'll be able to watch this then before tomorrow's class because we will pick up directly from the end of this and tomorrow's class. So, so great. So today we're going to start then chapter 26, which is the first official chapter when it comes to the next upcoming exam. And that's chapter again, 26. So first I'm going to talk about is what's an electromotive force. So an electromotive force is what we're going to call this curly E is a device that supplies some sort of potential difference via work. So what are some examples of this? So an example of this, first of all, would be something like we've seen often, and we've used often, is a battery. So let's kind of take a moment to kind of look at the way a battery works and see how this actually works. So, over to here. So, so this is your standard type of battery. Now, this is a battery that would represent something more like a car battery or a D battery or C battery or double A or triple A or even something like a 9-volt battery. So basically what this is it is two pieces of metal where these two pieces of metal are made out of different materials, maybe even carbon, right? And then I'm going to place these guys into some sort of electrolytic fluid or a dilute acid. So basically what happens is that the acid here starts to dissolve one of the two, which is this one over here. So this is what we're going to call the cathode. So as it starts to dissolve this metal, positive ions then from the metal as it's being dissolved will then go into the electrolytic fluid. That then is going to leave negative charges then onto the cathode, causing this guy to become negatively charged, which then makes the electrolytic fluid here a positive charge. Now, the electrolytic fluid doesn't really want to be positively charged, and because of Coulomb attraction, it's then going to start to pull the negative charges from then the other piece of metal into the electrolytic fluid, causing then that piece of metal then to remain positively charged, which is then what we call the anode. Now, this dissolving happens at pretty much a fixed rate. It doesn't really change too much over time, which means the ions going into the electrolytic fluid happens pretty constantly, while the anode ions, meaning the negative charge ones, which are moving then into the electrolytic fluid, also happens at a pretty constant rate, which then means that the potential difference then between the anode and the cathode remains pretty much constant all the time, right? As long as I have no current running through the system. So these then pieces of metal would be the pieces of metal that I would actually hook up my system to, so my wires to then run a current if I'm actually going to create a circuit. Or if I was talking about something more like a car battery, I would string a bunch of these together to then create the amount of potential I need necessary for a car battery. I think that's around 15 volts, but don't quote me on that. I'll have to actually look that up. But anyways, so again, this potential difference then basically remains constant because again, the rate at which all the stuff down here is happening remains constant. Now, once I then start hooking up a current through the system, so I then run current through it, what happened then is the amount of potential difference between these two actually decreases. And again, the reason for that is that now I'm pulling negative charges and positive charges from these cathode and this anode to make it run then through the circuit. But again, the dissolving rate and the pulling off of ion rate remains fixed, which means that the system can't really keep up with the demand that is necessary for the amount of current flowing through the system, which then causes this potential difference here to basically decrease. And we saw this in the lab. So we saw if we actually run a current through our D batteries there, the potential difference, what we call the terminal voltage, then decreases as I actually run current through the system. And we'll talk more about that next chapter, but basically it has to do with resistance, or what we call the internal resistance, as you saw in lab. But again, this is kind of the basic idea of the way that an old style battery works. Now, of course, this has nothing to do really with how your cell phone battery works or anything that's a rechargeable battery. That works more on a chemical process where I start off with, say, negative charges on one side, positive charges on the other side. And then here what you have is some sort of permeable membrane between the two, kind of separating the two. And then what happens then is that they start to intermingle. So the Coulomb attraction causes the positive charges to move to this side, the negative charges over here to start moving through this side, and the membrane just makes sure that it happens at a relatively fixed rate to, again, maintain that my potential difference stays about the same. And then what happens then is eventually there's going to become a electrically neutral system. So what happened is that, again, my positive charges, my negative charges will bleed through to each other enough that this whole entire system becomes electrically neutral, at which point in time your battery dies. So this is when your cell phone battery dies or your laptop or etc. So then from there you have to charge it. And then when you charge it, what you actually do is you use the charging system, which is typically when you plug it into your wall, to then force the positive charges back to one side and negative charges back to the other side to create that potential difference again by having positive on one side, negative on the other side, and then let the system run through again. So okay, this is basically the way that a battery would work. So a battery, again, is just one particular type of example of a electromotive force, or what we're going to call EMF for short. Call that guy EMF. Another type of example would be something like a generator. So this is another type of example. We could also have something like basically a crank. So for example, we could just grab a crank and spin that guy around. In that case, then we're using mechanical work to then turn it into electrical work. This could also be something like a hamster running on a wheel. Could also be hydrodynamic, right? So this could be something like a waterfall, which actually turns a crank, which then ends up creating electrical energy. Whatever it is, something that actually creates then a potential difference. Okay, so this is what we call an EMF. So these are all different types of examples of what an EMF actually is. But again, a battery is just one particular type of example of electromotive force or an EMF. So when we talk about EMFs, it doesn't necessarily we're talking about batteries. Again, we're just talking about something that supplies a potential difference. Now, the way that this works is that basically the point of the battery is to move positive charges from the negative side to the positive side. Now, what we know is that when that happens, or that doesn't actually happen spontaneously, because again, Coulomb's law says that the positive charges want to get as far away from the positive charges as possible. So basically what happens then is I have to do work onto the system to then move my positive charges basically from the negative side to the positive side to then let them go through the circuit itself. So let me kind of draw a rudimentary type of circuit. So let's say in this case, I have, here's the positive plate of my battery, here's the negative plate of the battery, and I have current, say, flowing through the system. Okay. So what happens is my positive charges here, because of Ben Franklin, we say it's positive charges moving, move through, and then they're going to be attracted to the negative side. So my positive charge will end up going here. Now the battery then has to do work on this charged particle to move it from the positive or from the negative side to the positive side to get it to go through the circuit again to then establish a current. So this is the point of the battery. So the point of the battery is to do work. So what we can do then is we can define what's known as the EMF or the electromotive force as then basically equal to the work per unit charge. So this is what we call the, the EMF. So it is the rate at which work is being done per unit charge, or the derivative of the work with charge. So we know this is basically true because, again, we know the change of potential energy is equal to the charge times the change of potential. Or if my potential is constant, this would then also be equal to the change in charge times then the potential. But we also know the change of potential energy is the same thing as the work. So in this case, I'm just looking at the derivative of the work with respect to charge, which is then equal to potential. So this thing actually is a potential and not a force. So don't let the name fool you that it is the electromotive force. It actually really doesn't have anything to do with force. It actually is just a potential difference. So this thing has units of. So good. So this is what we call, again, a battery or an EMF, electromotive force. So anything that, again, supplies a potential. So the next thing we're going to talk about is then capacitors. So capacitors are a very standard thing that you'll find in a lot of electrical systems or electrical circuits. And so let's talk a little bit about capacitors. So what is a capacitor? So we talked about this a little bit in lab. So we said was that a capacitor is generally two conductors. So here are my conductors, which are separated by some spatial distance of d. Okay? Now, what we're going to do then is we're going to take these capacitor plates, and then we're going to go ahead and hook this up then to a potential source. So my battery or my EMF, let me call that my EMF, which is then going to start to, again, drive charges through the system. So if then this is my positive side, it's going to then start pushing charges, positive charges, then onto this plate. So I'm going to get a positive charge onto here. Simultaneously, from the Coulombic repulsion, that's then going to take a positive charge from here, kick him off, and then push him back into the battery, okay? Which overall leaves a negative charge on this guy. All right? Then what it's going to do is it's now going to take another positive charge out of the battery, and it's going to try to put that then onto the system, onto this plate. But now it has to overcome the Coulombic repulsion to then get this charge onto here, because now I have a positive charge. I want to put another positive charge on. It doesn't want to go there thanks to the Coulombic repulsion. So the battery then has to do work over that to then put that charge on there. Again, that charge then is going to kick out a positive charge from here, cause that to go back into the battery, leaving then another negative charge on here. And this will keep going and going and going and going until eventually what's going to happen is I'm going to try to force one more charged particle on here. So let's say here's my last one that I'm going to try to force on there. But I have way too much charge on here that the battery can't overcome the Coulombic repulsion, at which point in time the whole entire system will stop. When that happens, then this is going to reach some maximum charge Q, and then this one's going to reach a charge of negative Q. So this is what we call capacitor. Now, this actually gives us information on what is the point of having a capacitor. Well, the point of having a capacitor then is that because every charge that I put on top of the capacitor plate has to have work done onto it to overcome this Coulombic repulsion, that means then that the point of the capacitor is to store energy. So this is its primary function. Its primary function is to store energy. And it stores energy because of the work done by the battery. Because the work done by the battery. So this is the primary entire purpose of a capacitor. So anytime you have a capacitor within the circuit, its sole entire job is to save energy for later use in the form of potential energy. So this is going to store some sort of stored potential energy for later use. So this is its primary function. Of course, it has some sub-functions as well. So what are some other functions? We're going to call that sub-functions. So other functions that this guy can have are, for example, this is your RAM in your computer. So when your RAM of your computer, or basically the memory of your computer, when this thing has the temporary memory as you're actually using your computer to do calculations or etc., what happens then is that the RAM is made up of a string of capacitors. So basically I have a string of capacitors, and whichever capacitors are fully charged, so let's say here's my capacitor and this thing is fully charged, then this acts as a 1 in binary code. But if I have another capacitor which has no charge on it, this acts as a 0. So this thing actually acts as your 1s and your 0s as you are actually using your computer. So this is a sub-function. Another sub-function then is that this actually acts as surge protection. So for example, if you use a surge protected strip, so if you have something that you're plugging in using a surge protecting strip, I have like 1,000 of them around here, but that's okay. We'll pull it out. What happens then is that it actually has a bunch of capacitors on the inside. So that way, if your house got struck by lightning, you get a huge boost in current running through the circuit. But the capacitors in there basically block this flow of charges flowing through the system, which keeps your computer and your iPad and then whatever else that you have connected to an outlet like your stove or your microwave or etc. It keeps them from basically overloading and then dying, right? Being fried. So these are some sub-functions then of capacitors. But again, the primary function of capacitor is to store energy. I didn't write a complete sentence there. Store energy. There we go. So again, it stores energy because, again, I have to do work onto the system by the battery to then get this thing to charge up, which means that here I'm then going to store an energy. So I'm going to have energy stored across the capacitor, but we'll talk about that a little bit later. So the next question is then, how does the amount of charge on the capacitor compare then to the amount of potential I'm running through the system? So again, let's think about that. So again, here, let's say I have, again, my battery attached then to my capacitor. So typically we just draw these as two parallel lines, where again, if this is the positive side, this becomes positive. This is my negative side, this becomes negative. So I'm just going to call this generically V for now. So this thing is going to store some sort of charge. Well, it turns out that if I plotted the amount of charge as a function of the potential that I'm supplying by the battery, such that when this thing reaches maximum charge, the potential across the capacitor will exactly equal that of the battery itself. Right? So I'm talking about a static situation in this case. So it turns out that if I plot these guys, there's actually a direct linear relationship between the two of those, which means that the charge is directly linearly proportional to the potential from the battery and from the capacitor. So this is actually equal to the battery potential as well. So great. Turns out then that the slope of the line is what we call C, meaning that the charge then is equal to C times the potential, where C is what we call the capacitance of the capacitor. Capacitance. So great. So from this tells me that my capacitance then is going to be equal to the charge per potential, or unit-wise, is the same thing as a coulomb per volt, which gets a special name, which is called a capital F, which is what's known as a farad or a farad or whatever it is you want to call it. But basically, it comes from, I believe it comes from Michael Faraday. So it's just short for his name. So this is my capacitance. Now, it turns out capacitance can actually be something that's very hard to calculate. What I mean by that is how I'm going to calculate my capacitance will actually depend on the geometry of the capacitor. So as long as I have a nice geometry, I can actually analytically calculate this. So for simple geometries, we can analytically calculate. Now, for non-simple, most of the time you actually cannot actually calculate it. For non-simple geometries, cannot analytically calculate, which basically means that it's basically difficult to calculate because you can't actually do the integrals. So what happens in that case then is you can't solve them in what's called closed form. So in that case, we have basically two options. Number one is you could either numerically do it, meaning you can use computers then to basically calculate what C is based off of approximation methods, or, which is pretty much easier, is you can actually just make a plot, just like here, and then measure the amount of charge versus the amount of potential you put on this guy, and then basically generate a best fit straight line and then extract what the capacitance is from there. In this case, you can plot Q versus V and extract Now, what ends up being interesting, and we're going to hopefully show this and by doing a couple examples, is that the capacitance is only geometrically dependent. So what do I mean by that? So what I mean by that is, again, if I go back to here, it turns out that the capacitance here doesn't depend on charge, and it doesn't depend on the potential. It only depends on the geometry of the capacitor, which basically means then that's what. So this guy doesn't depend on V, doesn't depend on Q, because again, we can actually kind of rationalize that because again, as I change V, I change Q. So those two change proportionally with each other. So it only depends on geometry. So the only way, kind of, to change C is to modify the geometry. This is the only way to actually change C. Now, it turns out there is one other way, and we'll talk about that later. It has to do with adding stuff to it, which isn't exactly cheating, but in a way it's cheating based off of what it is that we're talking about. But that's fine. We'll talk about it in a second. So good. So let's do a couple examples on how we actually geometrically, analytically calculate this, and then try to come to this conclusion that it doesn't depend on Q or V, that it only depends on geometry. So again, let's look at a couple examples here. So switch back over to screen here. Sorry for all the screen switchings. So let's look at this one. This is the easiest one we could do first. So it says here that basically, as you can see, we have a parallel plate capacitor where we have a charge on one side, which is positive, charge on the other side, which is negative. And then what I want to do is determine what is the capacitance of this thing called the parallel plate capacitor. Now, to make this simpler, what we know in this case then is, again, these guys are separated by, as it shows here, D, and then this is going to be my potential on A. This is going to be my potential at B. So in this case, we're going to integrate to going from this direction, from A to B, because we know that B is the high potential side and A is the low potential side, and that both of these two plates have exactly the same area. So good. So let's go to our, so good. So good. So let's look at this example. So again, I have a parallel plate capacitor. So in this case, I have my positive and a negative plate. So here's my positive charge Q. Here's my negative charge Q. Right. So again, let's draw some charges. Those are my positively charged. Right. This is my negatively charged. And again, we know that our electric field points from positive to negative, which means my electric field is going to point in this direction. Okay. So again, I'm going to call this side A, this side B. So what I want to know then is what is my change in potential, which then is going to be my potential at B minus my potential at A. And again, the reason I need this is because the capacitance is equal to the charge divided by my change in potential, or just my potential, if I call V at A 0. So in that case, that'd be Q over V. Or in this case, I'm saying VA is simply equal to 0. So good. So in this case, what I'm going to do then is I'm going to use our definition we used from last chapter and say that our change of potential between 2 points then is equal to negative the integral, in this case from A to B, of my electric field dotted by the differential length. Okay. Now let's just set up a coordinate system to make this a little bit easier. So I'm going to say then is that going in the vertical direction is Y, just for funsies. Now, what we know, remember, as we talked about in class, is that my electric field inside of parallel plate capacitors is equal to a constant, which points perpendicular to the plates and is going to point, what? In this case, from the positive plate to the negative plate, so it's going to be in the minus j hat direction. And remember we said is that my total electric field out here is 0. My total electric field down here is equal to 0. And my total electric field inside the plates is simply twice the electric field of one of these plates. Right? So in this case, since I know my electric field only points in the j hat direction, what that means then is I'm going to write my dl to then only point in that direction, meaning that my dl vector is then going to be equal then to dy in the y hat direction. I mean, again, in general, I could take point in this direction. This could be my dl like this, but again, I would have some x component, but I is only going to dot with x to give me 0, so I don't care about any other components that are perpendicular to it. So good. So that means I can rewrite this then as minus my integral from a to b of my constant electric field magnitude in the j hat with a negative sign, so it's going to make that guy positive. Where am I? Yeah. Dotted then with dy j hats, but again, j dotted with j is simply 1, so it's going to be the integral from a to b. I'm going to drop these vector signs because now it's just going to be from a to b of then e dy. Good. Where the difference between a and b is going to be what we're going to call d. Okay. So good, we know E is simply a constant, so it's going to come outside of the integral. So I get E integral from A to B dy, but the integral of dy is simply y. So it's going to be the same thing then as A times B minus A, but B minus A is simply D. Now, using exactly what this guy is, then this is going to be the same thing as what? Eta over epsilon naught, because remember my electric field magnitude inside is going to be eta over epsilon naught times D. So good. Now let's use this definition here. So this thing becomes then my capacitance is going to be Q over eta over epsilon naught times D. Now, at this stage, you may be saying, aha, it actually depends on Q, but it doesn't, because remember that Q is equal to the charge per unit area. So let's go ahead and substitute that in. So finally, what I'm going to get then is that this becomes Q divided by Q times D divided by epsilon naught times the area. Or my Q's are going to cancel. This term is going to move to the top because I have a 1 over 1 over. So finally, this is going to become epsilon naught times the area divided by D. So this is my capacitance of a parallel plate capacitor. Now, before I move on and do the next one, notice that, again, my capacitance here depends only on the area of my plates. Okay, so going back to here, this is my area here. And the spatial separation between the two plates, i.e. this distance d. So it only depends on the geometry. Now, just to drive this home a little bit more, let's go ahead and do our next example. So let's switch to the next example. Let me share the screen. Too many sharings, I know. So next one is this one. So this says, what is the capacitance of a cylindrical capacitor that consists of a wire or cylinder of radius A surrounded by a coaxial cylindrical shell of inner radius of B, which has a length of L. Good. So let's bring this one back up. So let's draw this. So all this is saying then is on the inside, I have some solid cylinder, let's say, right? So this thing is a solid cylinder where this then has a, let's call this then charge per unit length lambda, and this guy has a radius of A. And then I'm going to shroud this guy then with a coaxial cylindrical shell. So here's my coaxial cylindrical shell with its own radius of B, which then has, in this case, also the same charge per unit length. Okay. Now again, one of these guys has to be positive, the other one has to be negative. Ultimately, it doesn't really matter which way I go, but let's do it this way. So let's say my outside one is the positive one and the inside one is the negative one. So that in this case, I know my electric field will then point in this direction, the direction of my electric field, pointing from positive to negative. And then, which means that the outside portion then is my high potential. Inside portion then is my low potential. I'm going to take my inside portion as A, my outside portion as B. And again, I want to integrate from high potential to low potential. So I'm going to integrate in this direction. So it's going to be my DL. Now, let's just remind ourselves. So basically what happens then is what's creating the actual electric field on the inside by Gauss's law is simply the cylinder. Not the cylindrical shell, but the cylinder. Because again, if I drew my Gaussian cylinder on the inside, let's say, what color haven't I used? Let's do that in red. So if I did my Gaussian cylinder on the inside, like this, remember it's only the charge which is enclosed, and the only charge enclosed between the inside cylinder and the cylindrical shell is the inside cylinder. Now, because of that, I also know that outside the cylinder, as we did with Gauss's law, is the electric field is then equal to lambda, which is the charge density, right? Divided by 2 pi epsilon naught r in this case, negative r hat direction because it's pointing radially inward. Now again, dl, as we talked about in class, dl is going to be, in this case, cylindrical coordinates. So it's going to be a complicated combination of both r hats, theta hats, and z hats. But again, since my electric field only points in r hat direction, that means the only portion of dr I care about is in the r hat direction, which means dl then I'm just going to rewrite as dr in the r hat direction. Right. So now let's plug this in. So this means then, again, that my potential difference between the two plates, which again is going to be the VB, minus VA, is then going to be, again, minus my integral from radius A to radius B of, again, my electric field dotted by the differential length. Now, again, here, this negative coming from here will cancel this negative. So this will become then the integral from A to B of then what? Lambda divided by 2 pi epsilon naught r hat dotted by dr hat, but again, r hat dot with r hat is just simply 1. So finally, this becomes then the integral from a to b, again, dropping my integration or my vector signs, lambda over 2 pi epsilon naught r dr, or since lambda over 2 pi epsilon naught is a constant, that tells me then my change of potential will then be equal to lambda divided by 2 pi epsilon naught integral dr over r from a to b. Now, integral of r1 over r dr, again, our pirate speak, is natural log. So this guy is going to become simply equal to lambda over 2 pi epsilon naught, natural log then of b over a, because again, I'm using, as we talked about in class, natural log of b minus the natural log of a is simply equal to the natural log of b over a. So that's where this term is coming from. Now, again, what I know then is that my capacitance then is going to be equal to the charge divided by my change of potential. But again, if I call VA equal to 0, then this is simply going to be the same thing as Q over V. So plugging that in, this is then going to be Q divided by lambda divided by 2 pi epsilon naught natural log of B over A. And again, you might say, aha, depends on Q. But again, remember that lambda is the charge per unit length, which in this case then is if this guy has a charge, it has a length of little l, as it says in the problem, which means that this is my length of little l. So this becomes Q divided by little l. So again, let's plug that in. So it says my capacitance then is going to be equal to Q divided by Q over 2 pi epsilon naught L, natural log of B over A. But again, here my Q's are the same, so I'm going to cancel my Q's. This term, again, will move to the top because it's a 1 over 1 over. So finally, excuse me, I get a 2 pi epsilon naught L divided by the natural log of B over A. So this is then my capacitance or my cylindrical capacitor. Now, again, looking at this, as we looked at in the previous problem, this thing only depends on L, which is the physical length of this guy, and it depends on the ratio then of the radii, which means, again, it only depends on the geometry. There is 0 dependence on the charge and 0 dependence on the potential. It only depends on the geometry of my capacitor. So again, the only way to change the capacitance of my capacitor is to change the geometry. Okay? If I don't change the geometry, I do not change the capacitance of the capacitor. Oh, good. So now it turns out that for manufacturing purposes, there's only certain types of capacitances that we can actually make. So what do I mean by that? So what I mean by that is if, for example, I wanted to make every possible type of capacitor anybody would ever need, what that means then is that anytime my capacitance that somebody needs is different by even say zero point 0.1 or 0.01, I would have to make a completely different capacitor. Right? Now, what that basically means then is that theoretically, I would need then an infinite number of different capacitors to be created. Because if I need one that is, say, 2 farads, and I need another one which is 2.01 farads, and then another one that's 2.05 farads, right? I would basically run into the point where I'd have to make an infinite number of different types of capacitors. Now, because manufacturing wise, that's going to take a long time. Material wise, that's a lot of material I have to buy to make these things, and I'm not guaranteed everybody's going to buy one of these. Then that basically means that that's a bad decision to do because at most I can make one capacitor for every type of capacitance ever possibly needed, which is just not good business, right? That's just a bad way to actually do things. So what we do instead is, for that reason, we only make a certain handful of different capacitors. And then if you want a different capacitor, then you have to create your own capacitor from pre-existing capacitors. So this is what we call adding capacitors in parallel and series. So capacitors, parallel, series. So basically, the point of adding these guys in parallel and series is, again, I can actually create new capacitances by adding these guys together in such a way to either increase the capacitance or to decrease the capacitance. So let's see what happens with each one of these different things. Now, so let's talk about each one. So first of all, let's talk about what's called series. So series is when I have a battery and connected then to a capacitor. So let's call that C1, the capacitance. Another capacitor, it's called that C2, and then another one which has its own capacitance called that C3, and I'm going to connect that then to the battery. So this is what we call series. Now, this is called series because the current which comes out, or the charge, if you want to think about charge, which comes out from the battery here, basically only has one choice and one possible direction to go. So it can go from here on to here, depositing a charge onto here. Well, that will then kick off a positive charge from the other plate, pushing that same positive charge then onto here. That's going to kick off a positive charge from the other plate, again by Coulombic repulsion, but that then onto this plate, causing it then to go back into the battery, which means that this will end up with a negative charge here, and then negative charge here. So ultimately what that basically says then is that the charge on this plate is exactly the same on this plate, which is exactly the same on this plate. So in series, the charge is the same. So again, series simply means there is no choice. You get chicken and that's it. Okay? Only option. Only option. Now, let's contrast that then with what's called parallel. Parallel, we're going to start with the same thing. I'm going to take a battery, and I'm going to run that then to this point here, and then I'm going to put branches. And I'm going to have this branch here, which is going to have a capacitor of C1. This branch here, which has a capacitor, say, of C2. And then this branch here, which has its own capacitor, which has capacitance of C3. And I'm going to bring them back together at this point, and I'm going to hook them back to the battery here. Now, what's again going to happen is what? I have my positive charge is going to come out, but now this positive charge, which is going to come out, so we use the same thing, is going to come and it's going to reach this point. By the time it gets to this point, it's going to say, now I have options. So this is what we call a junction, which is also called a node. So at this node or this junction, the charge then is going to go through one of these three legs. Okay. Now, the amount or which one the charge goes through is going to depend basically on the capacitance of that particular capacitor. Okay. So what do you kind of think about this, even though we don't really have anything flowing, but if you think about hoses and I run water through the hose, when it gets to a junction point it has different options of different ways the water can go. Now, the water is going to go in the direction at which has the least amount of resistance to it, or if you want to think about cross-sectional area, it's going to go in the one that has the greatest cross-sectional area. But all three of the hoses will ultimately have water going through it, but the amount of water which is going through it is going to be dependent on the size of that cross-sectional area. Here is kind of the same idea. So what's going to happen is maybe some of that charge is going to go here, some of that charge is going to go here, and some of that charge is going to go here. So what happens in this case then is that in general then, the charge here, Q1, will be different than the charge here, which is different than the charge here. Okay? So this is what we call parallel. Now, let me go back to series for a second. Now, for the series, what happens then is that because the charge here is the same as the charge here, which is the same as the charge here, but the capacitance here is different than the capacitance here, which is different than the capacitance here, that means the potential difference across each one of these guys is different, right? Which means that my potential difference here is going to be V1. My potential difference here will be V2. My potential difference here then is going to be V3. Now, contrast that then through the parallel one. So for parallel, what we know is that by the loop rule, the change potential through any loop has to be equal to 0. But here, notice I have 3 different loops, which means one loop is I can start off with the battery, I can go through here, run through the left leg, and go through the battery, which means if this has a potential of V, then this also has to have the same potential of V by the loop rule. Or I could go from the battery through the central leg, back to the battery, which means that again, by the loop rule, the central one has to have exactly the same potential as well. Or I could go through the right leg back to the battery, which means that again, this one has to have exactly the same potential. So what happens then is for parallel, the potential is the same. So in series, what has to be true is that the charge on each one of the capacitors has to be the same. But in parallel, it's the potential across each one of the capacitors which has to be the same. Now, what's the overall point? The overall point is that our claim is going to be that I can collapse or connect all 3 of these capacitors down such that they act as one capacitor, which is connected to the same battery. So in this case, I can say, well, these guys act as they have one capacitor, which is what I call the equivalent capacitor. Simultaneously, I can say, well, these guys here in parallel also collapse down to the point where they have one capacitor, which again is my equivalent capacitor, and the potential. So in this case, our claim is that we can combine these together in such a way that we have one capacitor connected then to our battery. Well, let's see how this works. So let's look at the series one first. Now, let's go back to you. Now, again, what I know is that since the amount of charge which is coming out in series here is identically the same, then that means the charge which is then going to be on this capacitor plate will be exactly the same, which is on any of these 3 other capacitor plates. Now, again, what I know is that the potential coming out of the battery then has to, by the loop rule, be split up through the 3 different potentials on the 3 different capacitors. But what has to be true by the loop rule is that the potential from the battery must then be equal to the sum of those 3 potential drops across the capacitors. So in this case, I can say then, well, my potential is then simply equal to V1 plus V2 plus V3. Now, using the fact that Q is equal to C times V, that means that V then is going to be equal to Q over C. So this is going to be the same thing then as what? So this is going to be Q divided by C1 plus Q divided by C2 plus Q divided by C3. But since all the Q's are the same, it's going to be the same thing as Q times 1 over C1 plus 1 over C2 plus 1 over C3. Now, let's go back to our claim. Our claim then is that, again, since this charge here on this capacitor, which is equivalent capacitor, is the same as each one of those different charges, And that this is the same circuit. So what that means then is that the potential across this one here, which is the V, must then be the same thing as that charge divided by the equivalent capacitor. So ultimately what this means then is that Q then is divided by CEQ. Now, since the two Q's are the same, I can get rid of those. So finally what I get then is that 1 over CEQ is equal then to 1 over C1 plus 1 over C2 plus 1 over C3, or in summation notation, this becomes the sum over I of 1 over CI, which means that my 1 over my equivalent capacitor is then equal to 1 over the sum of all my capacitors. Now, geometrically wise, let's kind of think about what's happening. So let's think about a parallel plate capacitor, where we said this was epsilon naught times the area divided by the distance. Okay? So basically, what you can think of is by stacking these guys then in series, what I'm ultimately doing then is increasing the overall distance between the two plates, right? Which means that as the distance increases, the capacitance decreases, which is ultimately what this thing does, right? So if I add numbers together inversely, what that ultimately does then is it decreases the capacitance. So if I wanted a lower capacitance than any of the capacitors at which it is that I have, I then have to add them all together in series to decrease the overall capacitance. Good. Now let's do the same thing then in parallel. In parallel, what has to be true then is that what? Let's go back to our picture. The charge then, which is coming out of the battery, Q, must then get split up into Q1, Q2, and Q3 by charge conservation. Meaning that, in this case, I'm going to start off with the fact that Q must be equal to Q1 plus then Q2 plus then Q3. Now again, using that Q is equal to C times V, this is going to be then C1 times V plus C2 times V plus C3 times V, because again, the potentials are the same. So I can factor that out. So this becomes V times C1 plus C2 plus C3. Now again, our claim is, again, the charge that comes out of here is exactly the same as the charge coming out of here, which means it's the same, which is the charge which is on this plate. And again, this potential here is exactly the same as the potential from before, which means that my charge then, I can then rewrite as CEQ times then the potential. Now again, since this potential is the same, because everything is in parallel, what I get in this case then is that CEQ is simply equal to C1 plus C2 plus C3, or again, in summation notation, this is then equal to the sum over all the capacitance. Now again, what this thing is saying then is that's what? Adding them in parallel ultimately increases the capacitance. So again, if I wanted a capacitance which is greater than any of the capacitors that I have, I need to add them in parallel so that way I ultimately increase the overall capacitance. Now again, I can think about this geometrically by again saying that C is equal to epsilon naught times the area divided by the distance. Now, from here though, going back to my picture, by adding these guys in parallel, what I can think is that they're actually being squished together, so I'm overall increasing the area. So in this case, my area is increasing, and as my area increases, my capacitance is increasing, which then matches the statement here. So ultimately, what this means then is that, again, if I want to increase the overall capacitance of my capacitor, I have to add them in parallel. If I want to decrease the overall capacitance of my system, I then have to add them in series. So ultimately, again, it's just going to depend on what it is that I actually want to do. So do I want to add them in parallel, or do I want to add them in series based off of the amount of capacitance that I actually need? So I'm going to stop here, and then tomorrow we'll start off with some examples of this, how we actually do this. These problems are actually pretty easy, but they can be kind of tedious, and you'll see why. But basically what happens is that we have to go all the way in one direction and then unravel everything we just did to then get the result that we want. But again, we'll see some examples of this tomorrow. So I will see everybody then tomorrow.